Hello everyone, again welcome back to the latest lecture session. Again a quick recap of what we have been up to. So we are talking about how to remediate contaminated groundwater. In that context we looked at a passive technique, which is the permeable reactive barrier, right? And in that context we looked at the relevant aspects and looked at the relevant design with respect to the thickness, yes. And how did we do that? By considering this particular PRB, or the permeable reactive barrier, to be a plug flow reactor. We looked at the relevant basics of mass balance, applied the mass balance, right, and then came about with a way to calculate the thickness required for a certain removal of the contaminant, right? So and then we moved on to looking at a particular case study, right? So we are again going to obviously spend more time on that in today's session, yes. So again, the objective is to familiarize ourselves with some of the aspects that you come across on the ground, and also look at some of the measurements, let's say, of the relevant variables, let's say, or the concentrations of some of the variables that are relevant, right? And then we are going to try to understand, let's say, the change in these variables or concentrations of these relevant compounds in the context of our background in the relevant chemical or physical or biological process, right? So let's go ahead with that. And I believe we are talking about contamination of a particular mine or a locality, let's say, in Fry Canyon, right, in Utah, right? And I think it was contaminated among other, heavy metals. We also had uranium, radioactive compound, let's say, right? And in that context, we did see that we had adsorption, and thus we would also expect desorption of the relevant uranium from the soil, right? And thus pump and treat may be not a good idea, and also it's radioactive, so taking it out of the subsurface and exposing the relevant workers or the people in that particular area to the radioactive substance or to radioactivity is not a good way or a efficient way to go about it, right? So in that context, we were discussing how to set up, or what are the aspects we need to consider when we try to think of setting up PRB, right? And for this particular context, we looked at groundwater flows, right? We looked at how the situation changes when there is rainfall and when there is no rainfall, or between the monsoon and non-monsoon periods, right? We know that the contours change. That's something that we looked at in the last session, yes. And also we considered the relevant aspects with respect to the different concentrations, yes, as in the maximum, mean, and minimum, right? And in that context, we briefly talked about risk assessment, something we touched upon and or looked at in the initial sessions, right? And what was that? For example, if we took the median, or let's say the mean value of uranium concentration, and look at the relevant, what is a risk assessment, right? Say, you are going to have one particular scenario. But obviously, if you consider the mean or the spread of this particular concentration, let's say, right? Then you are going to have a different profile. And in that context, I would like to recall you about the stochastic and deterministic approaches. Deterministic approach, as in for a particular variable like concentration of uranium, we considered, we look at point estimates like average, let's say. But obviously in the stochastic estimate approach, pardon me, we consider the relevant variables to be variables and look at distributions. Typically we looked at normal and log normal distributions and so on, right? So let's go ahead in this particular aspect. So here we have concentration in milli or micrograms per liter, ppb, right? And here we have different concentrations of the relevant contaminants, and here uranium, let's say the mean or median, pardon me, is around, I think, 800 or 900, let's say, right? 800 maybe. And the maximum, as you can see, is pretty high, maybe 15,000 or so, right? So again, maximum, minimum, 25th percentile, 75th percentile, and so on. So obviously, what's percentile now? When I say, let's say when I give out the scores in class, let's say, and I give out the mean and also 25th and 75th percentiles, because that will give me a generic idea about the spread. Obviously, I have standard deviation, but and when the at least for my case, when the sample size is small, I sometimes prefer this. Again, 25th percentile, what is that about? When what does that mean? That 25% of the relevant samples or the grades in that particular class were lower than that particular 25th percentile. Similarly, what does the 75th percentile value correspond to? Let's say that would mean that, let's say if I have 60 marks out of 100 to be the 75th percentile, that means that 75% of the relevant students in the class scored 60 or less, right? Again, that's something aside, I guess. So typically here in this case, people were looking at removing uranium here, right? And keep in mind, I think this was in late 1990s, 97, 98 or so, right? And people, that was the initial phase when people were looking at PRBs, yes. And since then, obviously, as I mentioned, or as we discussed, the application of PRB has taken off. So we are looking at one of the earlier cases of application of or field application of the PRBs, right? So in that context, what did they do? They chose different compounds, and conducted the relevant tests in the lab, yes, and then column tests and then field tests, right? So we'll go through that in relatively greater detail. So we did look at this, but quick recap again: uranium concentrations in subsurface, right? So as you see, this is, I believe, my contaminated area, right? And groundwater is flowing, I guess, in this particular direction, right? And I guess we have samples at different locations. For various reasons, we do, have what we say different concentrations of the relevant compound uranium, let's say. Again, these are soil samples, not the groundwater samples, and I believe they are ppm values, right? I think we did look at that in the next slide. So we have different well numbers or wells here, right? 1, 2, 3, 4, and maybe 5 upstream. So upstream one, obviously, as you see, the concentrations are relatively lower. If any were detected, it's possibly due to diffusion, let's say. The transport upstream, let's say. So what I'm talking about here is, let's say this is my contaminated zone and my groundwater is flowing in this direction, right? Typically due to advection, let's say, and dispersion, my particular contaminant will, let's say, move in this particular direction now, right? In this direction. But I guess you can, if you take a sample out here, you can still detect some concentration, let's say, depending upon the relative transport of the contaminant due to both diffusion and advection, let's say. Advection is flowing in one direction, but diffusion in the other direction. Again, keep in mind that diffusion is random, let's say, right? So what's the driving force here? It will always go from a place of concentration, a higher concentration, to a lower concentration. So if anything is observed upstream, typically it could be that it's the background concentration at that particular site, or if there are no such background, and the only source is this particular contaminated source, it could be due to diffusion. Anyway, let's skip that now. And then as you see downstream though, you have, what do we say, 4 samples, and you see the concentration in the relevant sediment, let's say, is pretty high, right? So obviously, as we discussed in the last session, if you are trying to look at pump and treat and such, then the time required for pumping out the relevant water, especially in the case when you have desorption and considerable quantity or mass of the contaminant adsorbed onto the soil compared to mass in the aqueous phase. This is the concentration or mass, let's say, in the aqueous phase, right? And this is the concentration in the or on the soil or sediments now, right? So as you can see, considerable mass is present in the soil or adsorbed onto the soil. So desorption will take place, and thus issues. So again, in that context, PRB is a much better idea. So reactive media, how did they go about that? So they looked at some literature, looked at the availability and some other aspects which we are going to discuss later, right? So they chose different or many kinds of reactive media and conducted preliminary tests, let's say, right? And I believe they are published, elsewhere. So you can obviously dig them up if you want to. And based on that, they, screened some particular modes of removal of this particular uranium. So one was with precipitation, or one mode is due to or by precipitation of an insoluble uranyl phosphate phase, let's say. So uranyl phosphate, okay. So this is precipitating out, let's say, right? And that's one particular case. Again, the key is that we have phosphate here, let's say, and we are trying to precipitate out. It's only precipitation, not degradation, let's say. And the second way, I believe, is due to zero valent iron. So first we are reducing it as an uranium from oxidation state +6 to +4. As you know, zero valent iron, right? Pardon me, can go to Fe2 plus 2 electrons, or Fe3 plus 3 electrons, right? Depending upon the extent to which the reaction proceeds, let's say. As you can see, zero valent iron is a reducing agent or an electron donor. It's giving out the relevant electrons. And as you can see, uranium is in its relatively more oxidized form of +6. So to go from +6 to +4, it needs electrons, right? The oxidation state is decreasing. What does that typically mean? It typically means that it's accepting electrons, right? So it needs an electron donor, only then will the redox process go through, and the electron donor in this case seems to be 0 valent iron, right? And subsequent precipitation, right? So keep in mind that some of the process that we are talking about are not as straightforward or as simple as we are discussing. There might be many intermediate steps involved, but it is believed that in the case of PRB with 0 valent iron, the process involved are reduction first and then precipitation, let's see, right? And then we have amorphous ferric oxyhydroxide. Ferric oxyhydroxide, again ferric, we already have it in its iron in its most oxidized form, so reduction is not an option here, obviously, right? So the key here is that you have adsorption and then the removal from groundwater. So you have this AFO, or the amorphous ferric oxyhydroxide, right? AFO as we call it here, and then the groundwater flowing through the particular PRB comes in contact with your particular AFO, and then you have adsorption of the relevant uranium onto the relevant AFO, I guess, right? So again, the three kinds of process were precipitation, right? The other one is reduction and precipitation. The other one is adsorption. Yes. So these three processes, they chose different kinds of material, as in different kinds of sources for phosphate, 0 valent iron, and amorphous ferric oxyhydroxide, and they conducted further lab tests. Let's look at what they are. So just a particular example here, though. So we have the source of phosphate in the form of bone char phosphate pellets. So I think this is from the relevant SEM analysis, or it's electron micrograph analysis, right? And the scale is given here. So as you see, you can look at the relevant structure, and also that it has sites for precipitation, let's say, right? Or it's pretty porous, and you have relevant sites for, and at a much lower scale, let's say, or magnifying it further, you have the relevant sites out here, let's say, for precipitation and such, let's say, right? Again, just to give you an idea about how it looks up close with respect to the phosphate pellets, I guess, right? And again, what was the sequence or chronology now? They conducted lab tests and saw that these three processes were relatively better, and for these three processes they chose different kinds of materials, let's say, right? So in this context, we are looking at batch uranium uptake on various phosphate materials, let's say, some of the other data, let's say, and on the y-axis here we have uranium uptake or milligram per gram of solid. So this is the concentration of the relevant contaminant, which is uranium on the solid, and here obviously is the dissolved uranium concentration, right? So here on the y-axis we have concentration on the the solid, or the concentration of uranium on the solid. On the x-axis, concentration in the groundwater. So where do you think the slope should be now? Obviously the slope should be higher, as in that you would prefer that the concentration of the relevant contaminant on the solid phase, which is your PRB material here, is higher, right? So if I look at that data and I see that bone meal, I guess, right, bone meal B1, bone meal B2 are performing relatively better compared to the other types of material, right? As in, what does that mean? They are able to have achieve greater removal, let's say. In this case it was precipitation, right, per per gram of the particular contaminant, right? So but as we looked at earlier with respect to that electron micrograph here, what do we look at? We see that surface area is of considerable importance here, right? So now we just looked at it with respect to per gram, right, uranium per gram. So instead of looking at it per gram, we look at it per surface area or per square meter of solid. So now how do you see the data transforming? Here we have a great spread, but now you see that a lot of these particular types of materials have similar performance or have exhibited similar performance. Keep in mind that both these data sets are the same, except that the y-axis is different in that the first case we looked at uranium per gram, and the second case we looked at uranium per square meter of the relevant PRB material, let's say, right? And in this case it's the phosphate material, I guess, yes. And thus, as you see, surface area plays a considerable role, or obviously is relevant. And let's say, depending upon that, you see that if when I normalize it per surface area or by surface area, you see that the performance is more or less same. There is not a great deal of difference. So the key aspect, as in the differing aspect with respect to or between each of these phosphate materials, what is that? Let's say it's the surface area now, right? But obviously, I guess people also need to consider that it should be also the per gram removal, because when you are putting it in a PRB, you can't have particles that are way too small or such too, right? And also it's per gram is what you are putting in. For example, when you have a particular volume, let's say, and you know obviously density of the PRB is a remarkable aspect. So thus again people look at what is this now, the per gram removal. But again, take home message is that surface area is important out here, right? So up next, so summary of the column results. Let's see what we have. It seems uranium breakthrough occurred. So what is this breakthrough about? As in, let's say I have a column of the relevant PRB material, and let's say I am passing the relevant contaminant here, and this is how it's coming out. So this is contaminant initial concentration, and this is the concentration, let's say, coming out, let's say, right? And I monitor this concentration of the contaminant leaving the particular column with time, let's say, right? So initially, let's say most of it might be adsorbed, right? You know, the compound, let's say uranium, let's say, can be adsorbed or, you know, precipitated out on the relevant material, the PRB material. But over time, what would happen though, right? Over time, you know, all the sites might be used up or such, and you are not going to have any more active sites, let's say, right? And then what do you see? That you would see that the concentration leaving the system or the column, let's say in this case, which would be in the field scale be similar to the PRB, right, would keep increasing, let's say. And then depending on the type of material, you can have a sharp breakthrough and it might reach C0 again, right? So this is the breakthrough that we are talking about. So uranium breakthrough and uptake by different phosphate materials for 12 milligram per liter uranium, dissolved uranium at pH 7. So this is artificial groundwater, right? Not the actual groundwater. All phosphate materials were diluted tenfold with sand, again because of issues with respect to porosity, except bone char pellets, let's say, right? So some were diluted with sand or a mixture of sand and phosphate material except bone char. So let's try to understand some of the data we have here. So pore volumes required to for 50% breakthrough. So typically, I guess again what we have here, typically instead of time and the x-axis, we have either the bed volume or pore volume, let's say, right? So this pore volume is nothing but, let's say, obviously the amount of space occupied by the voids or the pores, let's say, right? So when I say pore volume, let's say, it means that these many runs of, for example, let's say I have 100 meter cube, let's say, and let's say 60 meter cube is occupied by the relevant pores, let's say, right? And I'm looking at this particular graph again, C, and here pore volume, let's say, right? So I have 1, 2, 3, 4 or so. What does that mean here? 1 means 1 times 60 meter cube, 2 times 60 meter cube, 3 times, 4 times, right? So how much volume that would be similar to the pore volume, how much volume of water which is similar to the pore volume, let's say, has passed through the relevant column now, right? Again, something for you to understand here. Instead of time, how much pore volume can it take? So what does that give you an idea about? That gives you an idea about how much volume of water can it or the column treat, let's say, before you observe breakthrough, let's say, right? So that's something out there. So here you can compare that and you see that typically bone meal, as we discussed earlier, seems to have better performance, and also slightly bone char pellets. This is something we looked at in the previous graphs, right? So you see that bone meal typically did better. Yes, and that's what you see out here too, bone meal, and uranium uptake at 100% breakthrough. As in, what does this give you an idea about? When you have 50% breakthrough, so 50% of C0, 50% of C0, let's say 50% of C0, how much volume of water was it able to treat, let's say, right? So here, as you see, bone meal was able to treat a relatively larger volume of water, right? That's this particular set of data now. And what is this data going to give me an idea about? Uranium uptake at 100% breakthrough in terms of milligrams of uranium per gram of solid, right? So at 100% breakthrough, which is this particular case, let's say at 100% breakthrough, right? At 100% breakthrough, what's the maximum or what's the concentration of the relevant uranium on the particular material? So obviously again, as you can see, it's relatively correlated. Obviously, I'm going to see that for bone meal it's relatively higher out here, right? Again, that's something in line with what we observed here, right, in both these two graphs. Yes, and that's something out here. So let's move on to the next aspect. Again, just data with respect to breakthrough of uranium in bone char column, bone char though. So as I mentioned earlier, we have column pore volumes here, right? Column pore volume. So what does this particular data mean, data point on the x-axis mean? It means that 50 times the column pore volumes have been passed through the relevant column now, right? If pore volume is x meter cube, so 50 times that particular volume has been passed through the column, right? So obviously here I see breakthrough somewhere out here maybe, right? C by C naught ratio of effluent concentration to influent uranium concentration. So obviously breakthrough is somewhere out here, right? When C, the effluent concentration is the same as the influent concentration, right? Again, this is the relevant profile out here, but this is typically not a great profile because complete removal or such was observed only for a relatively smaller volume of water, but for most volume, let's say you had some level of breakthrough. And here if I see that 50% breakthrough occurred at a relatively lesser particular column pore volume, I guess, right? So that's something that we need to understand. Again, what's happening here? So out here, let's say all the uranium that you are passing through your column is adsorbed or precipitated onto the relevant site on the bone char, let's say, right? But slowly but surely though, as you see here, the relevant sites are relatively less available, let's say, and now you see that you do not see complete removal in the effluent, but you see some uranium appearing in the effluent now, right? And again, that keeps increasing as you have less and lesser number of active sites, let's say. And again, there are different models. Obviously, one is the linear model, most simplest, but that's, as you can see, this is probably not linear. And then you have typical models like Langmuir or Freundlich. These are the equilibrium models that give you an idea about what we say the relationship between the concentration of uranium on, let's say, or any other compound that's adsorbed, let's say, on a particular solid phase to the concentration of that compound on the or in the aqueous phase. As in, we have, let's say, one of them to be Q equal to K C to the power of 1 by n. Q is the concentration of the contaminant on the solid phase, and C is the concentration of the contaminant in water, let's say. So what is this giving me an idea about? It's giving me an idea about the equilibrium relationship between the concentration of contaminant, what we say, in the or on the solid phase, and the concentration of contaminant in the aqueous phase. Again, some other aspects for you to understand here. And again, but the key aspect with these, what do we say, adsorption, desorption, or precipitation and then release is that, or dissolution is that, let's say I have groundwater, let's say, and my PRB is out here, the contaminated groundwater is flowing through. And let's say as it flows through, the relevant compound is adsorbed onto the relevant material here. And now the groundwater leaving the system doesn't have uranium at high level or has no uranium, let's say, okay. But what would happen, let's say, when all the contaminated groundwater has passed through, you now are going to have uncontaminated groundwater coming in contact with your relevant PRB material, which has now the contaminant adsorbed onto the material now, right. For example, let's try to also understand it mathematically. You have Kc to the power of 1 by n, right. So there is a relationship here, right. So initially, let's say the relationship, let's say the C in the water, let's say, is such that adsorption takes place now. But let's say now the contaminant groundwater comes in contact, so C in the water is less than the equilibrium value. So what will happen now? It will desorb from the solid phase into the aqueous phase, right. So your uncontaminated groundwater will now have uranium or can have uranium depending upon the desorption properties of that particular what do we say PRB material. So that's what we see here. So we have release of uranium from bone char column similar to the material that we looked at earlier. So again we have C by C naught effluent to influent. So here the uranium inflow, or there was no more uranium from out here, and here you have column pore volumes. If I look at the scale here, keep in mind that this is for 200, the uptake of the relevant contaminant, which is uranium, from the aqueous phase or from the water onto the solid phase, require relatively less, what do we say, pore volumes compared to obviously desorption, but still as you see here, you have desorption here, right. So, you see that this is the ratio of effluent to influent uranium concentration, right, and now you see that there is desorption out here, C by C naught here, right. So, we have a case where we had I guess the system had breakthrough out here, and then they stopped they are not putting in inflow anymore, but just pumping water through that. But obviously, you see that there is concentration or some concentration of uranium coming through this uncontaminated water here, right. So, what does that mean? You have desorption here, right. So, you can observe desorption out here. So, also if we look at the estimated uranium concentration on the solid, milligram per gram of solid, let us say, right, the dotted line. So, what do you see here? Slowly but surely the amount of uranium present on the solid is also decreasing, right. What is obviously happening now? This dotted line, what is it telling you? That it is coming down or decreasing now, right, as in the concentration of the uranium on the relevant PRB material is decreasing, right. What is it, where is it going now? It is obviously changing phase into the aqueous phase, and that is what you see here. So, when we look at the type of PRB material, obviously we also look at the effects of desorption, let us say, right. So, that is something we need to look at. So, keep in mind that that is one of the factors as in desorption that obviously is considered when you evaluate the relevant material, just for illustration purposes I brought up this particular data. So, again some more what do we say, data that would allow for relative comparison. So, you have uranium concentrations in 3-day batch tests, and what do we obviously have? Final dissolved uranium concentration in ppb, right. So, on the y axis you have the final dissolved uranium concentrations in ppb, and on the x axis you have different materials now, right. So, obviously what did they do? They did batch tests as in no flow coming in or going out, and they had different kinds of compounds, PRB material, what let us say in that were in contact with contaminated water contaminated with uranium. So, obviously after 3 days, let us say, what would you want? Let us say you would want the material to absorb more of it, and obviously the concentration of the relevant uranium or the contaminant in the particular water in contact with this PRB material should be low, right. So, typically then these particular, what do we say, types of materials did well, maybe some obviously you can rule them out here, right. So, let us see if we read that right, final dissolved uranium concentration in ppb, right. So, obviously the lesser the better, right. So, let us move on. So, again one other what do we say, data set, uranium concentration in effluent from column experiment, but unlike the case where we looked at phosphate relevant material, we are looking at the iron relevant materials, which are 0 valent iron and the amorphous ferric oxyhydroxide, right. So, one is the AFO ferric oxyhydroxide and sand, where the key what do we say, removal was due to adsorption, right, adsorption, that was the mechanism for removal. And for the one with 0 valent iron pellets, right, say what was the pathway? That the uranium was first reduced and then precipitated out, right. So, this was the pathway. So, let us look at the comparative data. First we have AFO and sand, right, ratio, again ZY foam pellets and sand, right, again different ratios here. Concentration of uranium in the influent was 2000 ppb or 2 ppm, I guess, right. So, what do we have on the y axis now? Dissolved uranium concentration in microgram per liter. We are talking about the effluent here obviously, and here we have volume of the relevant water that is passed through the column. Earlier we had pore volume, let us say, or came across the term bed volume, that is something else or something different from pore volume, but here they express it in terms that slightly unusual but easier to understand, volume of the water that is passed through the column here. So, what do you see here? As you keep passing volume, what do you say, you have your column here and you are passing water through here. So, this was at 2 ppm as we looked at here, 2 ppm the inlet concentration, and C is what we have out here. So, this is C here, right, and C, I guess is 0 or almost 0 until considerable volume. And then for the case of the ferric hydroxide or oxyhydroxide case, you see that the concentration has started to increase. So, what does that mean? Their breakthrough, let us say, I mean, we haven't reached breakthrough because it's still 200 ppb and we started out with 2000 ppb, right? So breakthrough has not yet occurred, but you see that now the concentration is no more 0, but that some of the particles are now leaving the system, right? Or it's going to approach complete breakthrough or 100% breakthrough though. But the key aspect here is that if you look at the zero valent iron based system, the green data points, let's say, it still hasn't shown it's still able to remove all the uranium from the relevant influent, and the effluent is treated pretty well, as in depends on the method detection limit, but looks like they are saying it's 0 or below detection limit, right? So here you have, or this allows for relative comparison, but the key aspect is that it's not just the material but the process that we need to look at. Here let's say the earlier case, we have an adsorbent ferric oxyhydroxide, right, upon which the relevant uranium is being adsorbed onto, right? In the second case though, you have reduction and then precipitation. So obviously different pathways, and looks like the sites, we are out of sites here, right? And here the relevant process is still going through or holding strong, right? Again, obviously one key aspect is the ratio of the relevant compounds here, right, with respect to sand. Yes. So let's move on now. Obviously let's try to summarize some of the aspects that are going to be relevant, let's say, when you need to choose your final PRB material now, right? Obviously availability, as in locally available, or is it easy to source if not locally available. Cost, obviously cost is an issue, yes. Permeable than the surrounding aquifer material, this is a key aspect obviously, right? So if it's not permeable, what's going to happen? It, as in the PRB material is not permeable, what's going to happen? The groundwater will flow around it, let's say. So either you mix it with a more porous material, let's say, or such, depending upon the kind of porosity or the hydraulic conductivity. So that's a remarkably important aspect. So something that we haven't discussed in great detail though, but it should be logical. Structural strength, so resistance to compactive crushing when placed in the ground, right? So that's something that obviously you need to look at. And then extent, rate and duration of uranium removal, this is something we have looked at in great detail. Extent is in, let's say, the maximum, how much can it remove. Rate, as in, let's say, is the desorption from the relevant water relatively fast or slow, and also the duration of required for removal, but I guess these are relatively slightly correlated. And then mobility, let's say, right? So once it's removed from the relevant groundwater, is the compound or the type of removal process decreasing the mobility, or again can it still, or can the relevant uranium still have some mobility? For example, looks like the tendency, we are looking at tendency of AFO to form mobile colloids now, right? So looks like with respect to AFO, even after removal, let's say, you have some mobile colloids being formed, so they can be transported further because they can leave the system, right? So that's something to be concerned about. What's it now? The tendency for the material to move with the groundwater. And then potential for re-release of uraniums, as in desorption, that's something we looked at with respect to the column studies. And detrimental effects on groundwater quality, such as is pH being affected, or we have way too high concentration of iron or phosphate in the groundwater that has left the PRB or passed through the PRB, right? So these are the generic aspects, and again we look at some of the details, let's say, again relate to the relevant applications. But in the next session, what are we going to look at? As I mentioned, let's say we are going to look at the actual placement or data from gathered from actual placement of the PRB in this site, right? So I guess I'm running out of time, and with that I'll end today's session, and thank you.